we're going to prove what's called the first derivative test. And what it says is, if f of x is differentiable on the open interval AB and f of x is continuous on the closed interval AB. Well, let me not say if. How about we say given that? Okay, now we have two statements. If f of x, if f prime is greater than 0 at each point in AB, then we know that f of x is increasing. Then f of x is increasing on AB. And 2 is just the opposite. If f prime is less than 0 at each and every point in the open interval AB, then f of x is decreasing on AB. So we have two things to prove. So proof of the first one. So we are told that f prime is bigger than 0 for all x in AB. So let x1 less than x2 be 2 points in AB. 2 points. We'll get this right. Let it be 2 points in AB. So what do we know? We know that by the mean value theorem, that f of x2 minus f of x1 over x2 minus x1 is equal to f prime of c for c in AB. Okay. Now, we know that f prime is positive for all x in AB, including c. Okay? So, we know that f of x2 minus f of x1 over x2 minus x1, this is positive. Why? Because it equals f prime of c, which is positive. Okay? Since x2 minus x1 is positive because x2 is bigger than x1, that means that that's positive. Well, if refraction is positive, we have a fraction, and it's greater than 0, it's positive, and the denominator is positive. I mean, you just have to be able to fill in this elementary school answer. What should the sign of the top be if the fraction is positive and the bottom is positive? The answer is positive. Why? Because if it were negative, a negative divided by a positive isn't positive. The top has to be positive. Okay? So f of x2 minus f of x1 must be greater than 0, which implies that f of x2, the higher x value, is bigger than the smaller x value. That implies that f of x is increasing, because x1 and x2 are any 2 points in their interval. F of x is increasing on AB. Okay, I'm going to see one. Okay, so now we want to do the proof for 2. So that completes the proof of 1. The proof of 2, well, it starts off with f prime is less than 0. Okay, on every point in AB. The f prime is less than 0 for all x in AB. So pick x1 less than x2 in AB. Now, we know by the mean value theorem, there exists a C in AB such that f of x2 minus f of x1 divided by same thing we did before, divided by x2 minus x1, this is equal to f prime of C, which is negative. So this is less than 0. That is f of x2 minus f of x1 over x2 minus x1 is less than 0. Since x2 is bigger than x1, that implies that x2 minus x1 is positive. So if this is positive and the whole fraction is negative, that means the top is negative. Well, that implies that f of x2 minus f of x1 is less than 0, but that implies that f of x2 is less than f of x1. Here's x1, here's x2. F of x2 is below f of x1. The function has to be decreasing. That implies that f of x is decreasing on AB. It's important that you say the neighborhood. In fact, we can say it's decreasing on the closed interval. We can say that it's increasing on the closed interval. And this completes the proof of the first derivative test. If the function is differentiable and continuous, well, if f prime over some region is always positive, the function is increasing. If f prime is less than 0, the function is decreasing. It's not because your teacher said, every time f prime, or I say, every time f prime is positive, on an interval, the function is increasing. No, we proved it here. Okay, study hard.